everybody, welcome today to this so-called specialist video. I'm here together with my colleague Ron Noomen from the Spaceflight Department. Ron, well, you have all seen him, of course, in the first and second year. He is assistant professor, and well, one of the core activities for him is, amongst others, to teach mission geometry and orbit design in the master program and anything related to space and orbital mechanics in the bachelor. So welcome, Ron. Thank you for being here.
Thank you.
So we're going to talk today about mission design. So what is space mission design? Can you say something about that?
Yeah, it's a very, very broad term, clearly. Also, obviously, it refers to a design, a process. In this, I would say that the students, any design or design team, you're typically confronted with requirements from a customer. I want to see this and this happening. Requirements, there will be constraints, there will be all sorts of things that have to be traded against each other. And typically the design team is to come up with a solution, an optimal solution ideally, for this particular exercise. It will involve a trade-off, that's clear. You can come up with a number of options to solve this particular problem. And the emphasis is basically on making sure that you can achieve a certain goal. So for instance, an objective might be to design a mission to the rim of the solar system. Can we do that? Within what limitations? What will be the consequences in terms of delta V, in terms of cost, and so on and so on. And then it, of course, plays a role for the students, particularly in the midterm review, where you trade a number of options against each other, and to a lesser extent also in later phases of the project.
But what is crucial in this phase of mission design?
Typically, we have two elements of which I think that they're crucial. First of all, we have the instrument. If you don't select the proper instrument, then you cannot perform the mission, or you are unable to come up with the optimal results. And the second part is, of course, to make sure that the satellite is in the proper position to do the observations.
Okay. Well, you already hinted at when we were talking about the first question at the importance aspects of the orbit. But why is the orbit information or the choice of the orbit? Why is it so important?
Again, you have to, or the customer requires you to do certain observations. So for instance, if you are ordered to do a study on the changes in sea level or in the ice caps on the poles or whatever, you have to make sure, it's very nice that there's a globe here, you have to make sure that your satellite is overflying the poles, including Greenland and whatever we have. If you would be after deforestation, you're probably more focusing on mid-latitudes. So the choice of the orbit that you or that the design team makes is crucial for that. In addition to that, there's a very important derivative of that. The solution that you will provide for the orbit will have consequence in terms of propellant usage. You will do maneuvers in order to end up at the operational orbit. You will have to do orbit maintenance. You will have to take care of end-of-life situations and so on. All of that will translate into a certain delta V. Adding that up in the delta V budget will give you the total delta V, and that translates, use the rocket equation or whatever you have, that will translate into a propellant mass, and mass is one of the most crucial things. Cost will be the most crucial thing, but mass is typically the second most crucial thing for the design of any mission. And if you are making a bad choice when it comes to the orbit, there will be quite a big conflict with launch capacity and whatever you have.
I can also imagine that there are constraints coming from, let's say, the science package that you have on board, or the instruments that you need for operating your satellite. Given the instrument, the orbit follows. But on the other hand, if the orbit is constrained, then you have to select wisely the type of instrument that you need for your observation. So
Yeah.
can you say something about that as well?
Yeah, a nice example, for instance, is a communication mission. Traditionally, we do it with satellites in geostationary orbit. So they have very powerful transponders, very large, heavy transponders. At this moment, there is a shift to working with LEO constellations. And of course, you can do with less capable, less heavy instruments there. So there is a one-on-one connection between the instrument on one hand and the orbit that you choose on the other. Typically, also when it comes to the DSE exercise, there is no need to reinvent everything from scratch. Instruments can be stolen, so to say, from previous missions, but they will typically work in a certain range of altitude or otherwise. So it is important to be aware of that connection. Yeah.
Okay. Are there any specific pitfalls that you can think of when you are designing your mission or designing your orbits?
Yeah, in particular when it comes to selecting the orbit, a standard approach is to start your mission in a parking orbit. You launch from Kennedy or from Kourou or whatever. Your satellite is put in a parking orbit. That is an option at least. And then from there the satellite is left on itself and has to be able to perform all the maneuvers that are needed. So that might translate into a very big delta V. There is, and consequences for the propellant mass, of course. There is a smarter alternative, that is take advantage of the capabilities of the launch vehicle as much as possible. If the launch vehicle is able to deliver your satellite already in the operational altitude, say 800 kilometers or whatever you want, it would be very, very attractive. If the launch vehicle is able to put you in what we call a geostationary transfer orbit, so taking you to an apocenter at high altitude, why not use that? If the launch vehicle is able to put you on an escape trajectory, your purpose is to go to Mars or to an asteroid or whatever, why not benefit from that capability?
Yeah. Okay. Well, going back to my own student time, I seem to recall that there were many, let's say, rules of thumb to do mission design, but that will only take you so far. So I can imagine that you need, computer programs to design your mission, to a higher level of accuracy. So can we use existing tools, or do the students have to develop them themselves?
The proper answer would be a yes and no. Of course, there are existing tools. It would be very, very weird if the students would not use those tools. On the other hand, computers are straightforward things. They will produce an answer, and students have the responsibility, or any designer actually has the responsibility to make sure that the answers are correct, that we understand what the answers represent, and that we can use them in a smart way in our own design. So I would certainly ask, if I were a tutor, I would require from the students to do an exercise where they design if needed, initial version of a certain orbit calculation tool, Hohmann transfer, whatever you have. Do their calculations with that and check that against the outcome of such tools. Later on, when you do more detailed calculations and you trust your software, that external software, then of course you can go ahead with that.
So basically what you're saying is that even if the software is existing, you have to do some form of an acceptance or verification test.
Always.
To make sure that the tool can do what you actually require for your project.
Always, always, always. Again, if I were the customer, I would not accept any result as long as such a test has not been done.
Okay, that's clear.
Yeah.
Are there any tools that you can suggest that we can use, or is there anything that the faculty can offer?
Yeah, there's quite a bit available on websites from NASA, ESA, and whatever we have. I can mention, for instance, GMAT or Malto, the STK Systems Toolkit. Be aware that some of them are commercially available.
So licensed.
Licensed. We do not have licenses for that. Simply said, it's way too expensive. So the students might be limited to using the very basic publicly available version only. But I can imagine that for most of the applications that is good enough. In addition to software for computing orbits, there's also software available for instance, characterizing a debris environment or radiation environment. Check out in particular the ESA websites. They provide quite a bit of data on that. ESA, NASA, JPL, whatever you have.
Okay, and the faculty itself, I believe there is a tool called 2DOT.
Yeah, it's a great tool, really great tool. It's very capable. You can do the calculations to the last digit, so to say. But there's one particular drawback here. It needs quite a bit of experience before you can apply it in your own calculations. The master students, they use it for their projects. The PhD students use it in their projects. But they typically take a course first, and it takes quite a bit of time to come up to speed with that particular thing. So yes, this 2DOT tool is available, but I would advise against using it for a DSE exercise. It's certainly not plug and play. It's not intuitive, so rather use something else.
Okay, that is clear. Yeah, we have come to the end of it. So before I say thank you for being here, is there anything else that you can add?
I think when it comes to the DSE, I think one of the most important objectives is that students use what they have up there, right? So please be creative, be open-minded, don't focus on one particular solution too early, and most of all, enjoy. It's a great exercise. I've been involved in it for 18 or 20 years, and I've always had the experience that it is the best element in the bachelor. So again, do enjoy.
Okay, thank you very much.
My pleasure.